Well, thank you very much. First off, let me say how much I'm very happy to be here in Iran and at Amir Kabir University. I'd like to thank the organizers for inviting me, and I'm really looking forward to a interesting set of talks and some interesting interaction with all of you. Let me request, if you have any questions during my talk, please feel free to interrupt me. My talk is for your benefit, so if you have any questions or anything that you don't understand, I'd be happy to explain them for you, either during the talk or if you'd like to talk to me afterwards. I'd be happy to answer any questions. So the topic of the talk that I want to give today is about the problem of point location in computational geometry. Let me see if I can... Yes. Okay. So here's the question that I'd like to consider. We're given a subdivision of the plane into a collection of regions. For example, you can imagine this as a map with the the regions being defined as the boundaries of countries, and we would like to pre-process this into a data structure so that if I provide you with any query point Q, let's say, then I can very efficiently determine which region, in this case, let's say France, contains that query point. The question, of course, is I could obviously answer the question, in a very slow manner if I wanted to, let's say, evaluate for every one of these borders whether Q lies within that border. But the objective here is to answer the query as fast as I possibly can by pre-processing, storing the information in some kind of a data structure. So this problem of point location is used in lots and lots of various applications. The most common, perhaps, is things like geographic information systems. I would like to know, which country, which state, or whatever contains a given point. The other application that I'm very interested in, and one that I will be talking about in future talks, is about nearest neighbor searching. So in nearest neighbor searching, the question is, if I give you a set of points, which one of those points is closest to a given query location? So the way in which this becomes a problem in point location is if I give you the set of points that I want to sort of discover the nearest neighbor of, then you begin by building the Voronoi diagram of that point set. And now the question just becomes, which region of this Voronoi diagram contains the query point, right? So obviously, if I can solve the point location problem, then that'll allow me to solve the, the nearest neighbor problem by this reduction here. Okay, so today I want to spend most of the talk actually discussing a much simpler version of the problem, which is I'm just going to look at the one-dimensional version of the problem and talk about some interesting data structures for solving the problem in that domain. And then I want to consider the kind of the extension of this problem to two-dimensional space. Okay, so the one-dimensional version of the problem would be, well, if I want to subdivide the one-dimensional line into a set of regions, then the boundaries between the regions are just going to be a set of points. So I want to imagine that I have n points, and these n points will therefore define n plus 1 intervals between the points. And then the problem that I want to consider now is, now given a query point, which one of these intervals contains the point? Okay, so given a query point Q, I would like to identify, let's say, the interval between xi plus 1 that contains the point Q. Now, throughout the talk, I'm going to be making kind of a simplifying assumption, which is common in geometry, that will state that I'm going to assume that, let's say the query point will only lie within the intervals. It will never actually coincide with one of the points. Later in the talk, I might mention there are some interesting results that have to do with the, in general, one would allow for the possibility that the query point could either be within an interval or could be specifically equal to a point. And I want to know exactly which of those two events is occurring. But I want to talk about this, concentrate on this simpler version for now. So I guess, all of you know about, the standard technique for solving this problem that is, worst case optimal solution, which is I'm just going to build a balanced binary tree for this problem. So, imagine a tree in which the internal nodes are labeled with the points, the leaves are associated with the intervals themselves, and then I just want to minimize the height of this tree. And then, of course, the question then is, given a query point Q, then what I want to do is I just want to trace its path through the tree. So the solution obviously requires O of n space to store the tree. the query time is going to be O of log n in the worst case. And so assuming that I am just doing comparisons, let's say I'm not allowed to do, well, things like techniques like hashing are not going to apply for this problem, right? Because through hashing, I might be able to determine whether you're equal to x4, but I cannot determine whether you're between x4 and x5. So essentially the techniques that I'm going to be used have to involve some sort of comparison, and because they involve comparisons, log n is going to be about the best that I can hope for. Okay. So this we know. The question that's more interesting then is, this was the worst case complexity. What can I say in the expected case? Well, to talk about the expected case, I have to make some assumptions about the probability that certain answers are going to arise. So the idea here is, what if some regions are more likely to be accessed than others? Okay, so Manhattan, let's say it is very likely if I'm doing a GPS query for navigation, I'm much more likely to be accessing points that are going to be in a city. It's more likely that I access points in Manhattan in the US than in the Mojave Desert. I don't know what the corresponding analogy would be in Iran. More likely to access points in Tehran than, I don't know, imagine some part of Iran that is out in the middle of nowhere, right? So the idea here is that I want to imagine that each region, A sub I, okay, is going to be associated with an access probability denoted P sub I. Okay, and obviously the sum of the P sub i's should be equal to 1. And again, I'm going to be assuming that, let's say that the access does not occur to the point itself. So I can think of, I'm just imagining that I'm only accessing the intervals in between. And then, so in order to define the cost of such a thing given a binary search tree, I'm going to let d sub I denote the depth of, let's say, the leaf A sub I in this tree. And then the expected search time will just be the weighted average of all these values, right? I'll take the depth of the node, which represents the amount of time that it's going to take me to access that leaf node. And then I'm going to weight this by the probability of accessing that node. Okay? So this is called the external path length of the tree. The question is, given the P sub i's, I would like to minimize that quantity. Okay, so here's a simple example of this kind of thing. Right? Suppose I tell you that this region A0 is very likely to be accessed, has an access probability of 1/2, 1/4, 1/8, 1/16, 1/16. Okay, and I claim that let's consider this particular tree here, which, by the way, is, I claim, the optimal tree in this particular instance. But irrespective of whether it was optimal, you can evaluate its cost as follows. So the expected search time is, right, with probability 1/2, you traverse a distance of 1. With probability 1/4, right, you have to follow 2 links. With probability 1/8, you have to follow 3 links. And in general, right, if I were to extend this tree out to any number of levels, you'd wind up with a sum that looks like this. Well, this sum obviously is a well-known series that converges. The value in general will be less than or equal to some constant. So for this tree, although in general given n nodes, right, in the worst case, the best I can expect is logarithmic time. For such a strongly skewed distribution of probabilities, the access time is actually just going to be a constant. Okay, so this shows that you can do much better than the worst case time. So this suggests the following then computational problem, which you may have seen before, by the way. So my objective here is to first to talk about the one-dimensional problem and then to consider the generalization to the two-dimensional case. So given a sequence of points x1 through xn on the line, okay, with associated access probabilities, and again, I'm imagining the access probabilities are between the intervals between these points, then I want to construct a tree that minimizes the expected search time. Okay. Well, if you're an old man like me, you may know some of the basic results in this area. In fact, this was, I'm kind of embarrassed to say that, I was actually, at the university close to the times when this was happening. I guess I started my university when I was, I think this was in 1973 or so. So, I'm actually old enough to be around when this research was being done. So there's a very ancient algorithm, I guess, by Gilbert and Moore that solves the problem in n cubed time. And Knuth showed the problem could be solved in n squared time. In fact, these were some of the very first applications of dynamic programming algorithms. In fact, if you studied dynamic programming in your algorithms classes, this actually is one of the standard applications of dynamic programming to compute an optimal tree. I should mention that the assumptions that are made in these tree computations are that the tree is sort of a three-way splitting tree. You can either check less than, equal to, or greater than. And this was the assumption that Knuth had made in his work. Hu and Tucker actually showed that one can do better than n squared. And this was sort of a more clever implementation of the same dynamic programming process. So although in the dynamic program there are sort of n squared different sort of subproblems that have to be solved, Hu and Tucker were able to show that you don't have to actually generate all of those particular instances. You can actually build the tree more efficiently. The problem, I guess, is the following, that these algorithms for very, very large values of n are going to be too slow. The Hu and Tucker algorithm, well, I'm going to claim it's a little bit too complex. Actually, I don't know that Hu and Tucker algorithm is that complex, to be honest with you. However, there is a very, very simple alternative. The more serious criticism of these techniques, though, is that they're not going to generalize well to two-dimensional space. Okay? So even though they give you an idea of how to deal with a problem in one dimensions, the two-dimensional generalization is not going to follow directly. And I want to consider a simple algorithm that I will be able to generalize for two dimensions. Okay. So I want to... Oh, yeah, question. Going back, yes.
These are building the tree, but what is the query time?
What is the query time? So, I'm sorry. So these algorithms will compute the tree that minimizes this quantity here. Okay. So in other words, what you're minimizing is the expected search time given the probability of accessing the individual nodes. I should add, by the way, that the general version of the problem that is solved by these guys is they actually consider two probabilities. There's what is called the failure probability, which is if you miss one of the points x1, x2. And there's another thing called the success probability. So usually it's expressed as I give you the probabilities p0, p1, p2 of falling in the interval. And I give you the probability q1, q2, q3 of actually hitting. The sum of the pi's and the qi's is equal to 1. And then these guys will actually solve this problem in that particular context. And again, they'll come up with the optimal value. Okay, nice question. Okay, so I want to kind of give you guys a quiz to ask you what you think might be a reasonable answer. I'm going to suggest two reasonably good heuristics. In fact, I think Knuth suggests that in looking at this problem, both of these methods might be candidates for a good solution. Not necessarily an optimal solution, but a solution that would be, let's say, fairly close to an optimal one. Okay, so here's the idea. Remember, the points are xi. Every point sort of sits between two intervals. And the idea is, if a point sits between or close to an interval of very high weight, let's say very high access probability, then I want this point to be very high in the tree, right? On the other hand, if a point is sitting in regions that are very low access probability, okay, then probably it should be lower in the tree. Okay, so here was the suggestion for how one might build a tree in a very simple top-down manner. So heaviest first says, okay, let us first find the point xi that has the maximum induced probability. So you look at the interval on the left, the interval on the right, and you add those together. Well, you average those two values, okay? And then you say, okay, the point that has the highest such value, I'm going to make that the root of my tree. Then I get two subproblems, and I'm going to recurse on those two problems. Okay, so this sort of says the most important point should come first in my search. The second one says, okay, no, if you think about balanced binary search trees, the goal is always to maintain equal weight in the left subtree and the right subtree. Okay? So rather than going for the point that has the maximum weight, what I should do instead is I should try to split the probability mass as evenly as I possibly can. Okay? Understanding that with various probabilities, it may not be possible to get a perfect 50-50 split, but I'm going to try to be as close to 50-50 as I can. Once I have found that most even splitting point, then I have a problem I solve on the left subtree and then the right subtree. Okay. Okay, so let me give a quick example here. Same distribution I had before, so 1/2, 1/4, 1/8, and so forth. If I do heaviest first, well, I first compute the induced probabilities. So, for example, this guy will be the combination of, 1/2, 1/4, 3/8, 3/16, 3/32, and so forth, working our way down. So this guy will have the heaviest induced probability. This guy will become the root of my tree. right? Left child, well, there's only one interval over here. Right child, I recursively solve. This guy will have the next heaviest probability. Boom, boom, so on and so forth. I get exactly the same tree I had before. Claim before was that was optimal, so in this particular instance, this actually produces the optimal tree. Balance split, again, I'm going to look at the distribution here. I have 1/2 probability here. The total probability here is 1/2. So half and half, the best node to start with is this first node, x1. And as you can imagine, I'm going to get exactly the same tree. Here I'm going to split again 1/4, 1/4, and so on and so forth. So in this instance, both of these algorithms produce the best result. Okay? Okay. In spite of their apparent, like I say, they both seem like reasonably good ideas. My claim is that one of these ideas is actually very good, and one of these ideas is actually very bad. In particular, one of these heuristics can be arbitrarily bad. For certain distributions, it will actually produce, in some sense, the worst possible tree you could have. And the other tree is nearly optimal, meaning that actually it will be very close, within perhaps a constant factor of the best. Not a constant factor, actually a constant additive term of the best. And let me just ask, I don't know, anybody here who wants to be brave to conjecture which one of these two heuristics you think is good. You like the second one, the balance split. Okay, you made the right choice. Yes. In fact, so let me ask, well, actually, let me give you, so you are correct with respect to the answer. Let me ask you sort of why, why this algorithm here will, do badly. I guess it's probably easier to see why the bad algorithm is the bad algorithm. Do you have any thoughts about, what kind of a distribution would make that algorithm perform poorly?
When we have two near weights, and one of them can is a bit more, what it can make the trees very, very open.
Yeah, I think you have the right idea if I'm understanding you correctly. So if you imagine a scenario in which the weights are very nearly equal to one another, right? Then you know that the best tree to have would be a perfectly balanced tree, right? If all the weights were about 1/n, okay, well, plus or minus, right? There's, I guess, n+1 intervals. But if the weights were all about the same, then the best I could do would make a perfectly balanced tree. However, the problem is if I perturb the weights very slightly, I can make you generate whatever tree I want you to generate. Okay? And so let me actually go and look at this example here. So the example would be this. Suppose all the probabilities are nearly equal to one another, but I'm going to make them monotonically decreasing. So 1/n, okay, plus maybe an epsilon1, 1/n plus an epsilon2. Well, by the way, these don't add up to 1, but let's, don't worry about that. We'll fudge that later on. But what I want to say is suppose these epsilon values are very small numbers, right, much smaller than 1/n, and they're decreasing. So if I do the heaviest thing first, right, this guy is going to have the largest weight. He's going to come first. He'll get picked. Okay, then this guy will get picked, then this guy. But because all the weights are 1/n, really the best thing to do in the first place would have just been to build a perfectly balanced tree. Okay? So the problem with this algorithm is when you're close to a condition where you kind of, either choice would have been a fairly good choice to make. Okay? You can force this algorithm to make a very bad choice over and over and over again, and so you wind up with a very bad structure. So this tree is going to have, the search time for this tree is going to be, what do I want to say? This is going to be the most unbalanced tree. The search time for this guy is going to be O of n, not log n. And you can see why. For half of the searches, right, you're going to have to descend at least halfway down the tree. So this is going to be bad. Okay. Eventually, I want to come back to this question, which is this such a really bad heuristic? Okay. And you might look at this now and you might say, hey, wait a minute, you did not implement this very well. Okay. Actually, that's true. I didn't implement this idea very well. I want you to maybe think about this. Later on, I'll return to this question of how to do this perhaps better. Okay. To get to what I really want to show you is why it is that the good algorithm is, the balance partition is actually a good solution. And to do this, I'm going to introduce this idea of entropy. Again, this is a very standard notion, and I expect that most of you have seen this before, but just to be complete, let me describe the idea. So, given a discrete probability, the entropy is defined to be the weighted sum of the. This is oftentimes written as the negation of log base 2 of pi, or in this case, just the log base 2 of 1 over pi. Okay? And from Shannon's source coding theorem, that it is well known that the entropy is a lower bound on the expected cost of any tree. Remember, if I look at the expected cost, we're talking about the external path length. That is the weighted path length in any tree. In the standard, coding theory, there is no notion of order. That is to say that there's no notion that one child has to appear to the left or right of the other. So this lower bound certainly applies to our problem here. But I want to mention the fact that although Shannon's theory applies to any tree, we have an additional constraint, which is x1 has to be before x2, has to be before x3, has to be before x4. So we have this constraint on the trees that we can build. So this adds some further complication. And to illustrate this, I want to consider, I'm sorry, the font's a little hard to read here, but let me sort of tell you what it is. So this is 1/2, 1/4, 1/8, 1/8. Again, this is the same distribution I had before, sort of exponentially decreasing. Here's another one, but I've permuted these values around. So I have 1/2 here, 1/4, 1/8, and 1/8. And now if you build what I believe are the optimal trees for these guys, well, we've already seen this tree here. In this case, the entropy value is, if you compute it, 1.75. Okay. I'm sorry, this is not the entropy value. Oh, I'm sorry, this is the entropy value, and it actually matches the expected, the external path length for the tree. Over here, however, if you look at this tree and you ask sort of what is the best that I can do, my claim is, well, again, if you look at something like a balance, split rule, I have to split the tree, I guess, someplace. I think the most balanced split is actually here, let's say, okay, with about a little more than half the probability over here, less than half the probability over here. But if you compute the external path length for this tree, you find that the value is 2.0. Well, obviously, the depth is exactly 2. So this is what you would expect. But since the entropy for this distribution, notice it's the same distribution, right? 1/2, 1/4, 1/8, 1/8, 1/2, 1/4, 1/8, 1/8. Shannon's theory will tell you the entropy is the same. Therefore, 1.75 is the best that you can hope for. But obviously, if the order of the nodes is different, I cannot necessarily achieve Shannon's bound. However, Kurt Melhorn showed that the balanced split heuristic is actually nearly optimal. And Melhorn's analysis essentially says the following, that if I give you any probability distribution, okay, let us look at the tree that results by applying the balanced split heuristic. Okay, then here's the assumption. Obviously, the optimal tree will be no worse than the tree you get by the balanced split. Okay, so this is clear. And then by Shannon's theory, you can never do better than the entropy here. Okay, but the claim is that the balance value here will be of the following form: 2 plus some constant times the entropy. Okay, and in fact, so this is saying that you will, in general, get within a constant factor, of the entropy value. The 1.44 here is a bit of a, it's a little bit misleading. There is a variant of the algorithm that Melhorn gives that actually eliminates this constant here. So it turns out you can actually achieve the entropy value plus 2 itself. I don't think, though, I have to be a little careful here. It's either the error is in the analysis or maybe it's in the actual heuristic. I think there's a variant of the balance. No, I take it back. I think it's the balance split heuristic that achieves actually the better bound, 2 plus 1 times entropy. I think it's just that the proof that's given here is not quite tight. But I'd have to go back and look at this stuff. It's been a while since I've read them. Okay, so the question then, why is this algorithm a good algorithm? As I said before, it seems like a reasonable idea to do, to always keep the probability mass evenly balanced between the two subtrees. But it's easy to see that I can generate, there may be situations where, with something like this, I've got a huge probability mass somewhere in the middle of my distribution. Let's take a look at this. So, I may have a situation like this where I've got one interval that's got a very, very large probability mass, and now it is not going to be possible to produce a balanced split, right? So I'm weighting these not by the actual values, but imagine these are being, the size is proportional to the actual probability itself. So here, for example, any split you perform is going to be unbalanced, which means that over here, right, I'm not going to make very much progress. Okay? Melhorn's observation, though, is this can't persist. That this could happen once that you have a very unbalanced split. But if you look at the very next split following that, right, the very next split will be the case that I will then isolate this point as a leaf node, and I'm done with this guy. And the other two guys, though, the internal nodes, will actually have very low weight. So even though any one split can be bad, if I go down 2 levels, the internal nodes that result after 2 levels will always have low probability. And so this was the way in which it's stated. He says, well, let's take, there will be some constant delta that I'll, just a fudge factor. If I take any 3 internal nodes, so for example, U prime, and then think of U double prime as either being this node, or let's say this node, this internal node, okay? Then if you let W, and let's say W be the total mass in this case, W prime being, let's say, the mass of this guy, and then maybe the next guy, I'm sorry, these would be in order. So U double prime would be this node here, and W double prime being this guy. Then the claim is that either one of 2 things happens. Either W prime is going to be a constant factor smaller than U. So even you will get a balanced split here. In this case, this did not happen. But if this does not happen, then when you get down to W double prime, you will get delta squared. So in other words, either you will make good progress with the first split, or if you do not, you will make good progress with the second split. Okay. Good. Now I want to get back to the problem that I started with, which was the point location problem. How am I doing here? I'm about halfway through. Okay. So unfortunately, neither of these 2 heuristics really leads to a good solution to the point location problem. And let's say not directly. We're going to have to do a little bit of work on them. The problem has to do not so much with the solutions themselves, but it has to do with the question of how do I generalize a one-dimensional, point location data structure, that is a one-dimensional binary search tree, into a 2-dimensional structure. And I have to have some way of bisecting the elements, let's say. Okay, for those of you who've taken a computational geometry course, you know the answer to this question, I suppose. But in fact, there are actually a number of ways of solving this one. In fact, I should go a little bit farther, because I see Wolfgang is in the audience here. There actually are a number of ways, he will note, that there are actually in order to solve this problem, not just those based directly upon trees, but there actually are techniques for, other ways for searching within subdivisions. But let me comment that there are sort of 2 means that sort of seem natural to generalize the tree-based method. The first would be, well, let's put in a line, maybe a vertical, diagonal, I don't care, that's going to then split the subdivision in 2. Another way would be, well, in fact, why do I not like this? The problem is going to be fragmentation. You're going to start cutting edges of your subdivision. This edge is now going to be split into 2 edges. If I keep repeating this, I'm going to get lots and lots and lots of edges, and my storage is going to blow up. So what was going to be O of n storage may grow up to something much larger. That's not good. The other idea would be, well, rather than splitting just upon a line, how about if we use something like a path to split at? So what I'll do is I'll just follow a series of edges that will then split my subdivision into an upper half and a lower half, or a left half and a right half. And then this will, of course, not fragment any of the edges, so the space of such a data structure will be O of n. The problem is going to be the query time. Because in order to determine whether I'm above or below, right, I have to determine where I lie relative to this polygonal curve, and that's going to take me some time. Presumably I'd have to do, if there's k edges here, it's going to take me something like log k time to determine where the query point is, which edge overlaps the query point, and then I'm going to have to go above or below. So now the query time may blow up. This actually was a problem for many years. I mean, in computational geometry, there were a number of different data structures that were proposed for doing point location. And, about half of the results use this kind of general method. Another half use this method. Eventually, by the way, the solution came about by, actually, there were solutions that are successful using this method, somewhat complicated. There are solutions that use this method, somewhat complicated. The simplest method turned out to be one that used a very different approach. Let me explain what that approach is. So the approach can be viewed as reducing the point location problem to a little different problem. So we started with point location, but I want to reduce this to solving a different problem called vertical ray shooting. So vertical ray shooting is the following problem. I imagine that I take each one of these edges that label a region, and I sort of project it down and label the edge, the lower edges of this thing with this guy. So A is going to be associated with this, this, and this. C with this, this, and this. D with these edges. So in other words, you imagine you just project the label down. you get a labeling now of edges. And now given a query point, the vertical ray shooting query just says, okay, just imagine that a drop of water falls straight down from this point. What edge does it hit? Okay, it hits edge C in this case. So since the edge is labeled with C, I know that the region that Q is contained in is going to be region C. Okay? So if I can answer vertical ray shooting queries, then I can answer point location queries. Okay? Okay. So henceforth, rather than thinking of this as a subdivision, let me just think of it as a collection of line segments. Okay? That's actually a nice generalization. In fact, that sort of is good because, you know, the issue is, although the final result is going to be a subdivision, the intermediate results are going to not be subdivisions of the construction that I'm going to be talking about. So this is the reason for having this little bit of a generalization here. Okay, what's the next step? Well, again, for those of you who've taken computational geometry, you'll know, assuming you take it from the same book that I read, you'll know this technique of using a trapezoidal map as a method for converting vertical ray shooting to basically to a point location problem. So we're going to kind of go back the other way. So given a set of line segments, I can define a trapezoidal map as follows. For every vertex, right, I shoot a bullet path up and down until it hits a segment. Okay, this is going to break my region up into a collection of trapezoids. You know, vertical sides are parallel to one another. These trapezoids could degenerate into triangles and things like that. Okay. This thing is called a trapezoidal map or trapezoidal decomposition. And then now the kind of weird thing is this. I can now solve vertical ray shooting queries by going back, okay, and solving point location in trapezoidal maps. Now this sounds kind of crazy, okay? I just told you I want to solve point location. I'm going to reduce it to vertical ray shooting. And now I'm telling you, hey, you can reduce vertical ray shooting to point location. But the important thing is this. What have I gained? I've gained the fact that now I can do this not for a subdivision, but for an arbitrary set of non-intersecting line segments. Okay, that is sort of the benefit. Why is that nice? Because it says that I can use some kind of an incremental strategy where perhaps I add segments one by one, or I remove segments one by one, or something like this. With the subdivision, that's a problem because, right, when I add segments, you know, the intermediate results are not necessarily nicely behaved subdivisions, but in this case, I don't care about that. I just have a collection of line segments. Okay, so how do you build a trapezoidal map? Well, again, I apologize for those of you who've seen this before, but just to kind of review the idea, it goes as follows. You add the line segments one by one. Okay, in what order? Well, it turns out the best order, actually there probably is a best order, but a sufficient answer is just to add them in random order. Okay, okay, so how do we do this? We imagine that we're going to add the segments one by one. Let's suppose we have already added, you know, some number of segments. So I've added these five segments to begin with. I've built a partial map here. When I add the next segment, what am I going to do? Well, I do the following. First off, I identify the trapezoid that contains the leftmost point. Okay, and again, I'm going to solve that by actually a point location algorithm, but I have to apply that point location algorithm to the existing subdivision. And then I'm going to start walking through my subdivision. As I walk through, well, actually, I'm going to begin by doing the following. I'm going to shoot bullet paths for this segment. So that's going to create a new trapezoid, right, for this guy. Then I'm going to start walking. And whenever I walk, if I hit one of these vertical walls, then I have to trim it back. So in this case, the wall was, the bullet path shot up from this guy. Because of this segment here, right, the wall is going to now be trimmed to this point. Okay, similarly, when I hit this wall, it was generated by this point. The wall is going to be trimmed here. When I get to this wall, okay, it's going to be trimmed there. But as you can see, after I have done these operations, and I finally wind up with the right point, by the way, when you get to the rightmost point, you shoot bullet paths up and down again. Okay? The important thing is this, that I now have a new trapezoidal map. Okay? The total space of the trapezoidal map is O of n. This is an easy theorem to prove, I guess, you know. If the important observation, I'm not going to prove this, but the important observation is that if the segments are inserted in random order, then the expected time to perform this is going to be O of n log n. So you can build the data structure efficiently. And, but as I mentioned before, you need to apply point location in order to do this. That is to say that I need to be able to actually do a point location to determine where the segment starts. Once I know the starting point, the rest of the operation is pretty much straightforward. The cool fact is this, though. You can build an efficient point location data structure as you are building the trapezoidal map. And here's the idea behind how that gets done. Going back to the previous slide, you can see that sort of there are two kind of things that are happening here. The first kind of thing is I have to determine relative to a vertex whether I lie to the left or right of that vertex. And that's going to be done with this thing called a left-right node. So given a point P, this node will either discriminate that things lie to the left or right of that. The other thing that I'm going to have to be able to do, going back, is I have to be able to distinguish whether a point lies above or below a segment. Okay? And for this, I'm going to have another kind of a node, above-below node. Let's say I'll call this, I think they were called X nodes and Y nodes in the book by the four Dutch guys. But basically, in this case, I have a segment is what's being stored in the internal node, and I have, left and right child would be above and below. Okay? And then here's the assertion, and again, I'm not going to go into detail. For those of you who've seen the algorithm will understand this. For those of you who've not seen the algorithm, it's just going to be confusing anyway, but I'll just sort of remind you of the basic ideas. That what are the various steps? So first off, when I insert the leftmost endpoint, right, I'm going to split up this trapezoid into three pieces. There's going to be the stuff to the left, and to do that I'm going to have a left-right node relative to P that'll say, okay, this trapezoid X is to the left of that. I'm going to start generating, walking along the new segment. I'm going to have a segment node, and I'm going to have above and below for that. So Y and Z for that guy. Then, if the line crosses through a trapezoid, then I'm just going to have a above-below node to distinguish which side I am on that. And then finally, when I arrive at the last, right, this is going to occur some number of times as the segment goes from trapezoid to trapezoid to trapezoid. When I finally end at the right endpoint, then I'm going to have this, again, I'm going to have three trapezoids. I'm going to have a left-right node with, in this case, X is going to be the trapezoid on that side. And then I'm going to have above-below node for the segment S with Y above and Z below. Okay? The idea is when I put this all together, what I wind up with is a rooted, not a tree, but a directed acyclic graph. Why is it not a tree? Well, it's not a tree because there is some sharing that will take place. What I will do is every trapezoid is only stored once as a leaf here. But it might be that there's two different ways of getting, or in fact multiple different ways of getting into a given one of these trapezoids. So the paths will generally split, but again, if two paths, an example would be something like this. For example, this node Y up here could be accessed, from this node, but on the other hand, there could be a query point over here that may access this node Y from a different path. If that is happening, then there'll be another path leading into Y. So this is the reason why you get this DAG. But the DAG effectively stores what is called the history of the construction, which is why it is sometimes called a history DAG. And the claim is if segments are inserted in random order, then the expected worst case query time, this is kind of a funny term here. So worst case means that I'm going to be looking at the maximum depth in the tree. Actually, in fact, that's not even 100% true. What I actually talk about when we talk about the worst case query time is we fix a query point and we ask, sort of what its behavior is. But in worst case, what I want to imagine is sort of what is the maximum search time in the tree. And I want to do this in expectation over all the possible random insertion orders. Okay? Okay. Now let me go to the problem that I had started with before. How much time? Again, about 15 minutes. Okay. So this is a data structure that will do point location for us in two-dimensional space that is, in some sense, good in the worst case. Okay. What if I now tell you queries are much more frequent, in some part of the world than they are in other parts of the world? That is to say, some regions have very high probability of access. Some regions have very low probability of access. I would like to build a data structure that is sensitive to that. How would I do this? So here's what I want to imagine. I want to imagine that in you're given initially a trapezoidal map for the problem. Actually, you might stop me here and you say, wait a minute, you're lying to us. You told us initially that you're going to give us a map of the world, not a trapezoidal map. And you are right. I'm kind of cheating you here a little bit. I'm going to assume that you actually know the probabilities associated not only with the original map, but actually the trapezoidal decomposition of that map. And the fact that I'm lying to you here is actually the topic of another research paper that I'm not going to talk about, which is how do you do this for a general subdivision. But let's suppose that I give you the trapezoidal map to begin with, and for every trapezoid, you know the probability of accessing that trapezoid. Okay? Now what I want to do is I want to build a data structure whose query time, ideally, right, should be close to the entropy. Because remember, the entropy for any distribution is going to be the lower bound, right? As long as you have a tree structure, entropy is going to be a lower bound on your expected search time. Okay. So I want to kind of extend this idea I talked about before. How did we do that? Remember, what we did before was this. We said we have a probability associated with each interval, but what I'm inserting into the tree are not the intervals. What I'm inserting into the tree are the things between, right, the intervals. So I need a way of associating the probabilities not with the empty regions, but with the things that bound those. So here's the idea for how I'm going to do that. For every region, every trapezoid that has probability p sub I, notice that this region is essentially going to be defined by four things, right? There's going to be a segment below, a segment above, segment to the left, a segment to the right. How about this? If a region is important, every one of these things has to be inserted into my data structure, right? This has to be there, this has to be, this has to be, this has to be. If this guy has very high probability, I want all four of those things to be inserted very quickly. So let's do this. Let us assign a quarter of the probability to this guy, a quarter to this guy, a quarter to this guy, and a quarter to this guy. Now, in general, a line segment is going to be incident to many different trapezoids. What it does is it accumulates all the weight from all the trapezoids that essentially are touching it. And that's going to be the probability induced upon this line segment. So the idea is going to be this, that every trapezoid now is bounded by four segments. Every trapezoid is going to split its probability amongst the bounding segments. And then now, observe that that segments that have high weight, okay, are essentially going to be those segments that are incident to trapezoids that have high probability. They will be inserted first into the process, assuming I used a weighted randomized insertion algorithm, okay? I'm going to insert the segments, but now in weighted random order. So the bigger your probability is, the more likely. In the previous one, right, every segment was equally likely. They were just using a uniform distribution. Okay. And so here's the main observation to make, and this somehow is not too surprising, that if we consider a trapezoidal map with n segments, access probability distributions, okay, the observation here is if you build a point location data structure using this weighted randomized insertion algorithm, then you get the results you like. In particular, what you get is linear, let's say, O of n size for the entire data structure. Well, that's going to be true no matter how, I guess, you insert things. And the other part is going to be this. The running time now is going to be essentially a multiplicative factor times the entropy. Okay, 5 times the entropy plus O of 1. I'm not going to actually describe everything in detail, but let me very quickly give you some intuition as to what is going on and how you would analyze this algorithm. Let me take a quick look at my time here. Yes, maybe a few minutes left. So the analysis is based upon sort of this little game. Rather than dealing with probabilities, what we're going to do is we're going to think about the probabilities as being represented by little pebbles. Okay? So each pebble is going to represent, maybe some piece of the probability mass. And I'm going to assign pebbles to these segments. Okay? I'm going to sample the segments, the pebbles at random. Okay? So the notion is that segments that have very high probability will get lots of pebbles. Okay? I'm going to sample the pebbles uniformly at random. Okay? The first sample pebble associated with a segment causes that segment to be inserted. Okay, and then here's the main thing that you are going to need in order to get this result, which is that if a segment has an induced probability of pi tilde, then the claim is that the level at which that guy will be inserted into the tree will be about log of 1 over pi. And this is actually what you need in order to achieve the entropy bound. If this thing happens exactly at log base 2 of 1 over pi, well, you will get the entropy. Within a constant factor, you'll still be in good shape. Okay? And then the final observation is this, that in order to bring a trapezoid into existence, I have to bring its 4 defining elements into existence. Okay? And if a trapezoid has a high probability, well, because it's distributing lots of pebbles to its incident segments, those segments will be introduced at a fairly early level in the tree. So here's a brief illustration of the algorithm. Okay. And I'm just going to look at the one-dimensional example here just to illustrate the idea. So let's suppose that, let's suppose that these are my probabilities. I can't even read this now, so I'm sure you can't. But it turns out in this case the probabilities are all basically some factor divided by 24. Okay, so 24 is the divisor here. I have 3 over 24, 1 over 24, 6 over 24, 1, 1, 1, 1, 1, 2, and 4. Okay, what I'm going to do then is I'm going to map these guys into pebbles. So in this case, the 3 over 24 is going to get mapped into 6 pebbles. Right? The 1 over 24 is going to be mapped into 2 pebbles, 6, 12 pebbles, and so forth. The next step is I then redistribute the pebbles, right? Remember, you're going to move the pebbles onto the incident elements. So half of the pebbles are going to come from this side, half onto that side. So 3 of these guys are going to come over here. 1 of these guys is going to come over to here. This guy is going to wind up with 4 pebbles. Okay? Similarly, again, 1 pebble over here, 6 pebbles over here. This guy is going to wind up with 7 pebbles, and so forth. And then now what I'm going to do is, now that I have the pebbles associated with each one of these guys, I start drawing the pebbles at random. Okay, so pick a pebble out. Okay, anyone here? Pick a pebble. Okay, you picked this pebble. Good choice. Okay, you pick this pebble, so what that means is that the associated point gets inserted into the tree, or in the trapezoidal map, the associated segment gets inserted into the tree. Next, you pick this pebble. Okay, this guy gets inserted. Which pebble gets picked next? You know, perhaps this one over here gets picked. Okay, maybe this pebble gets picked next, but notice this guy's point was already inserted. So if I pick the pebble that was from a previously inserted point, I ignore it. Okay, that guy was already inserted. I don't need to insert him again. And I just keep repeating the process. Pick pebble, insert the corresponding point. Okay, eventually every one of these guys is going to be selected, and then I'm going to wind up with my, my tree at the end of the day. And again, intuitively why this works is clear, because if somebody has a very high probability mass, there's going to be lots of pebbles, and the probability of selecting those pebbles early in the process is going to be very high. Okay. Yes. So a random insertion leads to a balanced tree, so the expected depth is going to be exactly what you desire. And like I said, this was the term that showed up in the entropy bound. So if I can achieve this bound, then I will actually achieve the entropy bound. Okay. By the way, so let me get to my concluding remarks here. Yes, I guess I'm going to get back to this question that I raised earlier here. By the way, I should back up and maybe just check to see whether, you know, because I've sort of finished the main analysis here, there's not going to be much more detailed analysis. But, you know, do people have any questions about, you know, how this algorithm is being applied? Again, I haven't done the analysis in any level of detail here, but I hope you would understand or appreciate kind of the intuition behind the analysis here. Okay, so if not, let me go on to the concluding remarks here. So the concluding remarks are, we discussed these 2 different heuristics for building binary search trees. Okay, with the idea of producing good expected case query times. We showed that the balance split heuristic is nearly optimal. Basically, 2 plus some constant factor times the entropy. We presented this randomized incremental construction for trapezoidal maps, for point location and trapezoidal maps, and we showed that a weighted version of this thing generates a good expected case point location. Let me, by the way, make a comment about this guy. You'll notice that we said that the actual search, the running time was something like 5 times the entropy bound. An interesting question here is how close can you get to the entropy bound? In other words, is 5 do? There actually is a very, very complicated algorithm, okay, and I can say that because I'm a co-author on the paper, that actually gets you arbitrarily close to the entropy bound itself, 1 times entropy, okay? But the algorithm is ridiculously complicated and would never be really implemented. I think this algorithm, if you really did have, you know, you wanted to do point location with regions with different balance factors and things like this, you know, this kind of an algorithm would be a reasonable algorithm to perform. We showed that although the heaviest first algorithm was bad, I mentioned that I wanted to return to this question at the end. There is actually a very simple variant of heaviest first, which actually is inspired by this algorithm, right? Rather than picking the heaviest interval every time, what you do is you treat the weight of a node as being a probability, and you do a random, let's say a weighted randomized algorithm where you pick the nodes in order. If I go back to that example, I guess at the very, very beginning, let me go back. I wonder if I can zip back that far. No, this is going to take too long to go back with this little clicker here. Yeah. So let me mention, if you recall, I had this bad example where, if you remember the situation, if I made all the weights of the intervals almost the same, right, what would happen then? Well, the heaviest first would be forced to pick, let's say, the leftmost node first, and then it would go down. But if I did a randomized selection, right, this would not be the case. And if all these guys had about the same weight, then I would pick sort of a random one initially, and if I know that if I build sort of a random binary tree, it's going to be pretty close, at least within a constant factor of the optimal binary tree. So it turns out the randomized variant of heaviest first is actually a pretty good algorithm. There are a number of other problems that can be mentioned here. One question, of course, that I'm not going to say anything about is, well, what happens if you make changes to your map, if you add edges, delete edges, or things like that? Another question, and I referred to Wolfgang's work in this area. So there is another kind of general line of work, which is what happens if you're not asking just one query? So imagine, for example, you're carrying around maybe your GPS device, and you perform a query, and then you travel some short distance and you perform another query. And then you should travel some short distance and you perform another query. Now, you might ask, why should I start at the root with every one of these new queries? I knew where the last query point was. Presumably, the new answer is going to be close to where the last one was. Are there data structures that are sort of sensitive to, if I give you a history of queries, that are sensitive to the pattern of these queries? Okay? And it turns out there are better algorithms than these here, in the sense that they don't just restart the search at the top of the root, at the root of the tree every single time. What they try to do is they essentially try to work locally from the result that you previously had. And there are techniques for designing such data structures. And I guess with that, I am pretty much done. Yes, so thank you very much, and I'll be happy to answer any questions that you may have. Questions? Yes?
Last you distributed the pebbles like equally between the neighbors. So what if we have the probability linearly or bilinearly distributed between areas? So does it look like a good approach to distribute the pebbles equally between neighbors?
So I don't quite understand the question. So you're saying I distributed the probabilities equally to all the other, the four bounding sides. And you're suggesting that maybe I use a different strategy?
Maybe if we have the probabilities of queries on some parts linearly interpolated or bilinearly or by some means interpolated, there could be a better distribution of pebbles.
That is actually an interesting point that you're raising. So you're right. We sort of made the very simplistic assumption that the access to a given trapezoid is something which is, is just, fixed and known, and there is somehow no, further, insight that one can have into these things. But I think your observation is a very reasonable one, if I'm understanding it, that, the distribution is perhaps not just trapezoid by trapezoid, but in fact, there is an underlying geometric distribution that is going on. And if I have a very wide trapezoid, it may be that, the probability of accessing the left side is much more likely than the accessing the right side. Perhaps I shouldn't distribute the pebbles evenly. Perhaps I should, throw them more on one side than they are on the other side. And that's a very intriguing suggestion here. Short answer is I don't know the answer to that question, but it would seem to me as though, subject to an appropriate analysis, you could make the case that there would be, let's say, unequal distributions of pebbles that might actually lead to, to better performance, under the assumption that there is a more, you have more information about the distribution inside the trapezoid itself. Yeah. Other questions? Yes? Yes, so I mentioned to you that there was a ridiculously complicated algorithm. Okay, the ridiculously complicated algorithm is a deterministic algorithm. I can tell you generally that the structure, though, becomes very complicated. The way it works is it does a much more, it actually builds not kind of segment by segment by segment. It groups the segments into large collections of segments, okay? In fact, by large, I don't mean, it's not just a large constant, but it's a vector that depends upon n. and you build an optimal data structure for, let's say, imagine square root of n, segments. And I take these segments, I analyze them very deeply, I build the very best possible data structure I can for those, and then I recurse on the pieces within those things. So there is a way of doing this deterministically, but it involves a lot more work and effort to get it to work. The nice thing about this algorithm is it's very easy to describe, easy to understand, and easy to implement. But yes, if your objective is best deterministic algorithm, it can be done, but it requires more sophisticated methods. Other questions? Okay, well, if not, then I thank you very much.